In this video we're going to talk about Laplace's equation. There's not going to be any Python code in this video. There's going to be a kind of companion video covering the same sort of ideas but with the Python coding. Laplace's equation in two dimensions is this equation here, d squared f by dx squared plus d squared f by dy squared equals 0. Well, there's also a three-dimensional version where you also have d squared f by dz squared. But for the moment, we're just going to talk about a function of two variables, f of x, y, and we'll say it's harmonic if it satisfies this equation. And there's lots of applications for this. For example, it's important in electrostatics and actually also closely connected with the whole story about complex analysis in pure mathematics. So we're going to try and solve Laplace's equation with given boundary conditions. And it turns out that there's a kind of really natural interpretation of what Laplace's equation means. It just means that for every point x, y, if you look at the value f of x, y at that particular point, then it's equal to the average of f at neighbouring points close to x, y. It's not a very precise statement, but it's basically the slogan anyway. And if we discretize, if we're trying to solve it on the computer, then what we do is we just take any point in the xy plane, and it's got four adjacent points, one directly above, one directly below, one directly to the left, and one directly to the right, and we try and make it so that the value of f at every point is equal to the average of the values at those four neighbouring points. And the typical kind of way the problem is set up is you've got some region in the plane, and it's got a boundary, and you know what you want the values of f to be on the boundary of the region. So the region quite often will be a rectangle or maybe a disk, and so it's a disk. You know what's the values of f on the circle. It's the boundary of the disk, and you want to know what's the values of f inside. So we're going to have a look at a interactive demonstration that will help us to understand what's going on here. Okay, so here's the picture. You're supposed to think that this kind of dark band around the outside. We're looking at solving the equation on this disk. This disk-shaped region that's basically this kind of grey plane in the middle, and the boundary of that is marked by this dark band, and the height of the dark band is the values of of our function f that we want on the edge of the disk. So so our problem is to try and understand the values of f in the interior of the disk. And so as an initial guess, we've kind of just put we put all the values in the interior to be equal to 0. So that means that the values in the middle are not sort of matching up very neatly with what's happening on the edge. There's these kind of long strings here, which are the gap between what's the value we want and what's the value we've currently got. And so our problem is to try and adjust the values of the function in the interior so as to make everything line up neatly and to make Laplace's equation hold. So we have to. So the most obvious thing that we can do is we can just sort of replace every value at every point by the average of the neighbours. And if we do that repeatedly, then things should settle down. So here we are. Every time we click the button, we replace each value by the average of its neighbours, and things start to get a bit smoother, and it looks more like a nice curved surface, which could possibly represent a harmonic function. And you see down here we've got a little picture of what's going on. So you've got the red point here, which we're updating. We update it to be equal to the average of the four neighbouring blue points, and the formula is like this, that Zij becomes a quarter of Zi minus 1j, which should be the value here, Zi plus 1j, which is the value there, Zij minus 1 is the value there, and Zij plus 1 is the value there. Add those up and divide by 4 to get the average, and then we replace the value in the middle by that new thing. And if we keep doing this, actually here, so here we've got the step count. We've done 15 steps so far, and we've done 16 and 17, etc. And this is showing the root mean square error. Okay, the difference between the values of the height of the grey mesh and where it's actually supposed to end up being to make a harmonic function. It's still got an average of 0.34. That's not great. We can start taking more and more steps, and you can see that the mesh is changing very gradually, and the root mean square error is slowly decreasing. but we do have to take really rather a lot of steps for the error to decrease at all, and it's still not great. 0.2. I mean the sort of maximum values we're looking at here is sort of like 1 or something. So error of 0.2 is pretty bad error. And you can kind of see that there is an error by it's pretty clear that for this to be harmonic, you would expect that the value in the center of the disk should be equal to the sort of the midpoint between the peaks and the troughs around the edge. And you can see here that that's not happening. In the middle of the disk, it's still somewhat below the midpoint, and you take more and more steps, then the midpoint rises just very slowly, but it's going to take forever. This is kind of like the idea if you're sort of trying to approach a particular point, but if you're sort of terrified that you might go too far, then you're just going to take tiny steps towards that point, and it's going to be very slow. It would be better if you were willing to just maybe step a little bit past where you're supposed to be, and then you've got a better perspective on where the thing is that you're supposed to get to, and then you can maybe step backwards, maybe a bit too far in the backwards direction, but hopefully it might converge a bit quicker. So there's an alternative method for solving Laplace's equation, which is a bit more like that. It's called the overstep method. So we can let's go back to the beginning, and we'll do this overstep. Let's do a few steps of that. Okay, and you see that here we've only taken a few steps, and this is only with 14 steps, and we're down to an error of 0.2, and after here about 60 steps, we've got a much smaller error than we did with the previous method, down to 0.04 or so, and we carry on, and then after 70 steps, down to about 0.02, and we carry on until so we get to about 125 steps, we get to 0.014, and in fact that's about as good as we can get. If we wanted to get a more accurate answer, we would need to have a finer grid with more points in it. But with this particular grid, we can get down to 0.014, which is not too bad. So let's kind of try and understand what this method is doing. Okay. So the idea is, the value of a partition I, j is Zij, and then the average of the neighbours is Z prime Ij. Okay. Then we put Rij as the difference between them, so that's the Z prime minus the Z. And so the previous method, the ordinary step method, we just add this Rij onto Zij, which converts Zij to Z prime Ij. But for the overstep method, we don't just add Rij, but we add 1.9 times Rij, or parameter 1.9, it could be something a little bit different. But so it's going to be close to 2, a little bit less than 2. Okay. And so you add 1.9 times Rij to Zij, so you're kind of going further than you think you actually need to. If we just do that everywhere, then it turns out that doesn't work well at all. You kind of start oscillating wildly. You just go backwards and forwards, bigger and bigger jumps every time, and nothing will settle down at all. But it turns out if we do this kind of slightly cunning thing, whereas we only do this kind of extra adjustment for half the points. Okay? So at the even steps, this is this step here. We're going to update the odd points. Okay, by the odd points, I mean the points where I plus j is odd. Okay, and so those are marked by these kind of blue blobs here, and those are surrounded. Each blue blob is surrounded by 4 red blobs. These are the odd points, and then the 4 red blobs are the even points. And so we update the blue point using the average of the adjacent red points. Okay, and so that's what we do this step, and then the next step we do the opposite thing. We update the even points here, marked in red, using the average of the adjacent blue points, and we keep alternating every time. Okay, and so you can see what happens here. So firstly, of course, nothing's happening in the middle. This is a key feature of this method. We update each point by the average of the adjacent points, and if you're kind of in the middle of the disk, then the adjacent points still haven't changed at all. So the point you're looking at doesn't change. Right? Nothing the influence kind of propagates slowly from the edge of the disk into the middle. So for the first few steps, nothing's going to happen in the middle at all, but stuff happens around the outside. And because we're doing this kind of overcorrection thing, everything is kind of rather jagged, sort of close to the edge, right? You've got all these kind of weird spikes and stuff. But it turns out that's kind of temporary. We take some more steps, then everything kind of calms down, and the jaggedness kind of moves in towards the middle, and then around near the edge, the whole thing is quite smooth. And then we continue on and on and on, and so the smooth region gets bigger and bigger, and the rough region gets concentrated more and more towards the middle. And then by the time we get to step 40, it's mostly sort of influence is propagated right to the middle. We've got a bit of rough stuff in the middle there. Then we just take some more steps, then everything gradually smooths out. And again, by about step 80, down to an error of 0.019, and then go to about 120 steps to get to the optimal thing. Got this very nice smooth curve here, which represents a harmonic function.